centered around A. Well, thus far, we've been talking about Maclaurin series or about Taylor series centered around 0. But I can write down a power series for a function not centered around 0, but centered around some other point A. What I mean is, I could try to write the function f as a power series, n goes from 0 to infinity, some coefficient c sub n, not just times x to the n, but times x minus a to the nth power. Well, just like before, let's assume that f has a power series representation and then try to figure out what those coefficients must be. Let me be a little bit more precise, right? What I'm saying here is I'm going to assume this holds whenever x is, say, within big R of A. And assuming this is true, I want to figure out what these coefficients have to be in terms of the function f. So let me just write down the first few terms, right? When I plug in n equals 0, I just get c sub 0 times 1, because it's something to the 0th power, plus when I plug in n equals 1, I get c sub 1 times x minus a to the first power, plus when I plug in n equals 2, it's c sub 2 times x minus a squared, and then it keeps on going. Now what happens when I plug in a for x? So that's asking what is f of a. Well, in that case, it's c sub 0 plus, what's this term? It's just 0, plus, what's this term? Well, it's just 0, plus all the other terms are 0. So this is telling me that c sub 0 is equal to f of a. Well, another way to say that is that if I knew that this was true for values of x within big R of a, then I know what c sub 0 has to be. C sub 0 has to be the value of f at the point A. The next coefficient can be computed in terms of the derivative, but not the derivative at 0, but the derivative at the point A. Well, let's differentiate this and see what we get. So I'm assuming that this is true whenever x is within big R of a. So the same will be true for the derivative at least. So the derivative of f at x will be the sum, n goes not from 0 but from 1 to infinity, of the derivative of this, which is c sub n times x minus a to the n minus 1. And this is true at least when x is within that same big R of a. Okay, let me write down the first few terms here. Let's plug in n equals 1. I get just c sub 1 times x minus a to the 0th power, so that's just c sub 1. Plus, when I plug in n equals 2, I get c sub 2 times x minus a to the first power. When I plug in n equals 3, I get c sub 3 times x minus a squared, and then it keeps on going. And now note what happens when I plug in a for x, right? What's f prime of a? Well, it's just like what happened before. I've got c sub 1, but then this c sub 2 times x minus a, that term vanishes. This term here also has an x minus a, so when x is equal to a, this term vanishes. All the later terms vanish. This means that I can recover the value of the c sub 1 coefficient just by differentiating the function at the point A. And so on, right? Just like before, I can now write down a formula for the nth coefficient. So in general, what I'll find is that c sub n can be computed by taking the nth derivative of f at the point A and dividing that by n factorial. So let me summarize all of this. The Taylor series for a function f centered at A, or sometimes you'll see just the Taylor series around A for the function f, it's given by this. It's the sum, n goes from 0 to infinity, of the nth derivative of f at A, that's the big difference, divided by n factorial. Here's another difference, x minus a to the nth power. I mean, it sort of makes sense, right? The Taylor series around A is a power series around A, so it's got this x minus a to the nth term. But instead of calculating the derivative at 0, we're calculating the derivative at the point A.